Okay. So, last time we were discussing two random variables, that is the joint statistics, joint probability density, joint probability distribution and things like that. Okay. Then a question that a very important question, a very important point or property is rather the statistical independence of two random variables. That is, when can we say that the two random variables x and y, they are statistically independent. Now, to answer that, let us go back to some of our earlier discussions. Okay. Suppose we have got two probability spaces, one is S1 that has the outcomes say theta 1s, that is set of all outcomes, okay, and A be a particular outcome. Similarly, suppose S2 given, okay, theta 2 and B. Theta 2 is the set of all outcomes here, this is another probability space and B is a particular outcome. Okay. In that case, we have seen one result that the joint probability of this event, or maybe instead of calling A to be an outcome, it will be better or more general if we say A is an event, that is a set of outcomes, and B also is an event. So, let me erase it. Okay. So, what is A B? This is joint event, that is we have got both these experiments going on. Theta 1 was the set of all outcomes, theta 2 is the set of all outcomes, A particular event, B a particular event. A B means joint event, A occurring and B occurring simultaneously. What was this probability of this joint event? That we had seen was given by either like this P A by B into P B was equal to also P B by A into P A. In case you have forgotten, we can also see how it is comes. That is, suppose N is the total number of trials, out of these total trials, actually we are observing both, I mean outcomes from or events from S1 and S2 simultaneously, parallelly. Okay. Suppose on N A B occasions, event A B occurred, events A B occur, and on N A or say N B occasions, number of times, this also number of times, number of times the events A B occur, that is A and B occurring simultaneously, that is N A B, and N B is the number of times B occurs. Obviously, N B should be greater than or equal to N A B, because number of time B occurs means the event from the other space could be A or may not be A, but as long as the event from the space is B, it is incorporated, it is added here, right, it is part of this. Then you have seen that the joint probability of the event A B is nothing but N A B by N, which you can write as N A B by N B to N B by N. Now, if N is large, N B by N is simply the probability of B, which is here, and N A B by N B, what is it? N B is the total number of trials for which the event B is fixed, that is the event which is occurring from the other set, other space, that is B, held fixed at B. Under that condition, how many times we get A? N A B times. So, under the condition that B is fixed, what is the probability of A B occurring? That is the probability. This is a conditional probability P A by B. By the same logic, you can have P B by A into P A. Okay, that you have seen. And this works well. This works for the events, but here there is no notion of random variable, only events. So, in the context of events, we have already defined what is joint probability. Then we have said that two events A B, they are statistically independent if P A by B, or independent rather, is simply P A. And this is obvious. Suppose A and B are two such events that B really, I mean this probability spaces S1 and S2, I mean they are such, or the corresponding experiments or the contexts are such that they have no mutual influence, they are absolutely independent of each other. In that case, whether you find the probability of A by restricting the event from space 2 to B or not, you should get the same probability, because the other space has no effect on the outcome in the space S1, right. So, P A by B should be equal to P A, and in this case, in that case the joint probability becomes just the product of the individual probabilities. So, joint probability or probability of the joint event A B is nothing but the probability of the event A multiplied by the probability of event B. Okay, that is what we have seen that time. But now we do not have the events as such, we are speaking in the language of random variables. Okay. So, we have to define similarly what is meant by statistically independent random variables. Here we are giving x, y, two random variables, okay, x and y. Then we say that they would be statistically independent if the probability of the event, say x belonging to a particular set A along the x axis and y element of B, the joint probability y taken from some set A, sorry, x taken from some set A and y taken from some set B. This is on the y axis, this is on the x axis. The joint probability is nothing but the probability of x belonging to A multiplied by the probability of y belonging to B. Now, this should be true for any set A on the x axis and any set B on the y axis. Remember the word, notice the word A, any. So, if it is true that if I take any set on the x axis and call it A and any set on the y axis and call it B, then the joint probability of x occurring, x belonging to A and y belonging to B, if the joint probability is simply the product of the individual probabilities, that is the probability of x belonging to A multiplied by probability of y belonging to B, then we will say that x and y, they are statistically independent random variables. Okay. So, this is true for any set A excuse me, this should be valid for any set A from the x axis and any set B on the y axis. Okay. If that be so, then what happens to the probability distribution, joint probability distribution f x y, what happens here? Now, this means what is this? After all, this is nothing but the probability of x okay. we can easily extend the previous argument. This means x less than equal to capital X means what? That on the x axis I am going from minus infinity up to x. So, that subset of the real axis. So, x belonging to that subset, and here, so here capital A x is nothing but that subset of real axis. What subset? From minus infinity up to capital X, and x less than equal to capital X means x belonging to that subset A. Similarly, y less than equal to capital Y means we take a subset B on the y axis, B goes from minus infinity up to capital Y, and y less than equal to capital Y means y belonging to B. Okay. So, if x and y are independent, then using our previous argument, this probability is nothing but product of the individual probabilities, probability of x less than equal to capital X multiplied by probability of y less than equal to capital Y, but the first one is nothing but the probability distribution of x up to capital X, second one is the probability distribution of y up to capital Y, which means if two random variables are statistically independent, then their joint distribution is nothing but the product of the individual distributions. Same would hold for the probability density also. After all, what is probability density? P x y at capital X y is nothing but or let me just simplify the notation instead of writing so many, writing in terms of okay. This is nothing but, so I am now removing the subscripts and directly putting x, small x and y, the variables inside, because that makes just simple notations, that is all. This is a double derivative of this with respect to x and y, but we have seen that if x and y they are statistically independent, then this f x comma y is nothing but f x multiplied by f y. And if you replace f of x y, that is as, if you put it back here, then this simply becomes p x x here I am bringing back again x y subscript, because otherwise I am using the same notation p here, but actually this is one probability density, this is another probability density, these two functions are not same. That is why I am just putting a subscript x here and y here, just to indicate that these two are two defined functions. This is a density function associated with x, this is a density function associated with y, just for that I am putting the two subscript. Okay. Then suppose u is a random variable which is equal to nothing but some function g of x, and v is another random variable which is nothing but some function h of y, where x and y they are jointly random variables. Okay, they are random variables and they have got some joint density. Okay. Further, it is given that x and y they are statistically independent. Then we say that u and v, these two random variables also will be statistically independent. Okay. Why and how? So, I repeat the statement. Given this would imply u v also are okay. It is not very difficult to show, but we can easily show it. What is the joint probability density? Okay. Or maybe instead of density, it is better to work with distributions. So, let me erase this. Joint probability distribution of u v. What is this? This is nothing but the probability of u taking value less than equal to some number capital U, v taking value less than equal to some number capital V. Okay. Now, u is coming from x. X is a random variable, it can take any value on the real axis, and since we have given a function g which works on x and gives you u. So, let A be a set of on x axis so that for all x belonging to A, let me g x, there is u equal to g x less than equal to capital U. Okay. And another thing is implicit here which I am not mentioning, that is any x not belonging to A, for any x not belonging to A, corresponding u equal to g x is greater than capital U. So, I am basically looking at the entire x axis, I am collecting all regions for which g of x is less than equal to this capital U. That collection of all such regions, okay, is called A here. So, outside A on the x axis, in all region that is outside A or not belonging to A, corresponding u will be greater than capital U. Similarly, let B be that is whenever I am looking at this y axis, actually I am collecting all regions for which, I mean if you take y from those regions, v of that is h of y is less than equal to capital V. Further and collection of these regions is called B, and further if you do not take y from B, but from any other portion of this y axis, then the corresponding h of y, that is V, should be greater than capital V. Okay. In that case, this probability, that is probability of u less than equal to capital U and v less than equal to capital V, this event, this is equivalent to this event x belonging to capital A and simultaneously y belonging to capital B. So, probability of u belonging u less than equal to capital U, v less than equal to capital V, same as probability of x belonging to capital A, y belonging to capital B. Okay. But we have been given this condition that x and y, they are statistically independent. That means, this probability is nothing but product of these two probabilities. and x element of A means it is equivalent to small u less than equal to capital U, because only when small u less than equal to capital U means that is if and only if x less element of A. So, this and these events are same. So, this probability is nothing but is equivalent to probability of, and by the same logic this is equivalent to the probability of V less than equal to capital V, and by definition this is the probability distribution of U and this is the probability distribution of V. So, this means that U and V they are also then statistically independent. This is why I wanted to, this is what I wanted to prove. So, I repeat, if x and y they are statistically independent random variables, then a function of x and a function of y also are statistically independent random variables. Then I move to this topic okay. Two random variables are given x and y. Okay. So, they can take any value, that x y pair can take any value along the x y plane, but they will be called circularly symmetric random variables if the joint density, that is joint density, it neither depends on x alone or not depends on y alone, but it simply depends on the distance of the point. There is, if there is a point here say x y, the distance of this point from origin, if this density it depends on the distance, that is square root x square plus y square, then x and y will be called circularly symmetric random variables. In this case, you see, if I draw a circle with the same radius, then at all points on the circumference of the circle I have got the same density. So, it is circularly symmetric. Now, suppose it is given that excuse me, given and they are also statistically independent. Then this would mean x y they cannot have any other density, other probability density, but they have to be Gaussian, that is they are Gaussian. Sometimes they are, I mean this Gaussian is also called normal distribution. So, you can say Gaussian or normal, 0 mean, equal variance. Okay. That is the joint density. Since they are statistically independent, after all there will be the joint density will be product of individual densities. Individual densities will be Gaussian with 0 mean and variance for both of them will be same. That is what we will prove now. But for that x y should not only be statistically independent, they must be circularly symmetric. Then their joint density or their individual densities for that matter are Gaussian. They have to be Gaussian random variable. There cannot be any other probability density possible. Okay. How? Okay. So, the joint density P x comma y, when you write it in terms of x and y, density is given as this function, but as I told you x and y they are circularly symmetric. That means, this density depends only on square root of x square plus y square. So, if you or r. So, if you express it as a function of r, it takes a defined form, this function it is no longer p of, it is no longer in terms of p, you can express it as a defined function, that function I call g. That is equivalent to g r, this is r. But we are given this fact that x and y they are statistically independent. So, g r is also product of these two. Again I am putting the subscripts x and y just to differentiate between the probability density for x and probability density for y, okay, because I am using the same symbol p for both. Okay. Now, see one thing, if I want to carry out this differentiation g of r, and therefore, it depends on x and y both. So, the partial derivative of g with respect to x, I can write it as d g d r, it is d because when you write it as a function of r, it is a function of single variable. So, no question of partial derivative, but usual derivatives. Okay. Then del r, here del comes because r is a function of x and y both, it is a function of two variables. So, del r del x, and what is del r del x? We have seen that r square is x square plus y square. This means twice r, if I differentiate this side with respect to x, twice r, then del r del x, that is equal to twice x dx, which means del r del x is nothing but, sorry, not dx, which means del r del x is nothing but x by r. So, what I get here is x by r dg dr, okay, which I call g prime r. That is the derivative of g r with respect to r, that is what we get. Okay. Now, we are giving this result g r is equal to, so long I took g r and just differentiate it, noting that r is this. I saw that differentiation can be, the partial derivative of g with respect to x can be written down like this, dg dr del r del x, and del r del x is x by r. But we are also giving this side g r is equal to p x x p y y. So, if I take the partial derivative of g r with respect to x, then I do the same thing on the right hand side. Okay. So, I get del g del x, which is on one side equal to this, on one hand equal to x by r g prime r, this also equal to p x prime x, that is the derivative of p x x with respect to x multiplied by p y y. Okay. So, let me write it down again clearly here. Or for that matter, you can put a 1 here and bring x here. Divide both sides by g r. Divide both sides by g r. So, this becomes 1 by r and this becomes, what is gr? Gr is p x x multiplied by p y y. So, p y y will cancel. So, this side becomes 1 by x then comes something very interesting, some interesting interpretation that comes out of this equation. Consider this. This point I call capital X 0 and this was our starting R x y, this x was coming here. Now, you see, look at the left hand side, this fellow, this is independent, this is just a function of r, right, and the radius of this circle is r, this is r. So, at any point on the circle, left hand side retains the same value, which means if I am at this point where x equal to capital X, okay, where x equal to capital X, I get the same value. Okay. So, at x equal to capital X, this function and therefore, this side. So, this function gives a value, okay, which is same as the value I was getting here or here or here or here. So, let that value be something, and now for this x at this particular point, for this x, right hand side was giving a value. If I now go on moving on this circle, I get other values for x also, okay. But whether I am having x here or here, I mean whether I am taking the x for this point or for this point or for this point or for this point, okay, this ratio has to be same, because left hand side is not changing. And what is left hand side? Left hand side is given by its value at this point, which means this ratio does not change. Whether I am here, here, all these points, that is whether I am moving on this circle like this, okay, its value does not change. Okay. So, that means this is a constant. Okay. If this be a constant, if this be a constant, that means a constant equal to alpha. In fact, alpha should be negative, that we will see. That means g prime r by g r equal to alpha r. G prime r by g r can be written as that is g prime r by g r is actually this, and this from our definition is alpha, I mean alpha r. Obviously, d of g dr of ln gr means first you differentiate ln gr with respect to g. So, you get 1 by gr, then g prime r and that is equal to alpha r. So, ln gr will be the integral of this. Gr will be exponential of that. Okay. So, what happens? In fact, I should have put the integral limits here, alpha r square by 2 say plus some constant c, okay, some constant say c. So, integral goes from some initial point to r, which means g r will be u to the power this entire thing, and u to the power c will give rise to a constant. You can call that constant capital A, which means g r is nothing but some constant A times e to the power alpha r square by 2. Okay. And we know r square is x square plus y square. So, it is nothing but A times e to the power so, you can easily see that x and y they are Gaussian, I mean because the dependence is in this form exponential, okay, exponential and the power of 2 comes and exponential of that is coming. So, alpha is obviously minus 1 by sigma square. So, alpha actually is a negative quantity 1 by sigma square and individual densities. And what is capital A? Capital A should be such that is we have now got into this constant say A1, A1 we know what it is 1 by root 2 pi sigma. Similarly, P y y say A2 okay. A1 A2 product should be equal to capital A. So, A1 is 1 by root 2 pi sigma and this is 1 by root 2 pi sigma. So, it should be 1 by 2 pi sigma square, otherwise it does not become a probability density function. Okay. So, you see this form immediately suggests that is a product of two Gaussian probability density functions, 0 mean, that is why x square is coming, no x minus mu whole square, just x square, and alpha is common, which means same variance, and the product of two Gaussian densities means joint density is nothing but product of individual densities, which means they are statistically independent. Okay, and that is true, that is already given. So, what I wanted to prove that each is actually a Gaussian random variable with 0 mean and both have equal variance, that is proved. Okay. So, this is an interesting property for jointly Gaussian variables. Okay. Now, when you are discussing just a single random variable, we consider an important topic, that was function of a random variable. Okay. That is given x and its probability density and a function g x, how to find y equal to g x, how to find out the probability density of y. Okay. So, we worked out various examples, we found out some relations and all that. We want to extend the same concept, okay, to the function of two random variables now. That is, given a function z, given a variable z as function of two random variables g x y. Okay. That time previously I took y axis the vertical axis for y and horizontal axis for x, and I could easily plot the function. Here there are two variables. So, I would suggest that you consider one axis for x, another axis for y, and take the vertical axis, that is the one which is going vertically up from this plane, consider that to be z. So, it is a 3-dimensional plot, 3-dimensional plot. Okay. So, I have to find out the probability density of z, or maybe the probability distribution of z, say, to start with. That is, I have to find out f z capital Z. So, capital Z is some number given to us, but what is f z capital Z? That is probability of small z taking value less than equal to capital Z. So, what I will do in the xy plane, suppose this is the xy plane, I will find out the various regions for which, I mean region such that if you take x and y, this pair from within those regions, then corresponding z as given by the formula of this function becomes less than equal to capital Z. These regions may be connected with each other, may not be connected. Okay. Maybe one region is this, another here. Okay. Together I call it dz. These two together, so I call it dz. Okay. This is x axis, this is y axis. So, within this z is less than equal to capital Z, within this zone z is less than equal to capital Z, together is dz. So, obviously, this event that small z less than equal to capital Z, this is equivalent to this event that x and y, this pair is belonging to dz. Remember, I have collected all such regions in the x y plane, all such regions for which the corresponding x y pair give rise to a z satisfying z less than equal to capital Z. Okay. So, that is why you can make this statement that the event z less than equal to capital Z is equivalent to the event that x comma y, this pair belongs to this region dz. So, obviously, the probability of z less than equal to capital Z is same as the probability of x comma y belonging to dz. Okay. Which means this is nothing but P of x y belonging to dz, or which is nothing but, you can take the double integral over dz P x y dx dy. Small p x y is the probability density. Okay. This is the probability density. So, you get the probability distribution of z from the probability density of joint probability density of x y by this manner. Okay. And how about the probability density of z? This was probability distribution of z. How about the probability density of z? Okay. That is, how about this would mean for this we consider delta dz be an area x y plane such that whenever x y belongs to dz, sorry delta dz, delta dz, this give rise to this is equivalent to small z taking values between capital Z and okay. After all, what is this probability density for this random variable z? It is nothing but the probability that z takes values between capital Z and z plus dz. That probability will be given by this probability density times dz. That is a general that we have already seen. But since z is coming from x y pair, I find out in this in x y plane an area, we call it differential area delta dz. So, that whenever x y falls in delta dz, okay, we have got this relation satisfied. Okay. That means, what is this probability is nothing but same integral, but this time integral over delta dz p x y dx dy. Okay. Let us take an example. If we cannot complete it, we will continue with the example in the next class. Consider a very simple case, straight line z is equal to x plus y. Consider a line x plus y equal to 1 or x plus equal to z. You can see at y equal to 0 this is z and at x equal to this is z. So, as the value of z increases, that is as this line moves further outward, value of z also increases. So, it is a plane, okay, going further up, it is a plane going further up, because as these intercepts increase, the value of z also increase. Okay. A simple case. So, how to find out the probability distribution of z? Okay. So, what do we do? Take a particular line, say. Okay. If this value is y, then what is this value? Z minus y, right? Okay. So, probability of x y lying within this is what? We integrate the density. So, with respect to x from minus infinity up to z minus y, and then we move y like this. Okay. That is, first along this line, along a particular line from minus infinity to which point? Z minus y. Dx along this line. Okay. But this is only one particular line. Now, I have to move this line from minus infinity up to infinity. Okay. So, I will be here on this line up to this, next line up to this, next line up to this, and likewise up to this because of the limit. Okay. As y moves, this limit also moves leftward, and I span this entire area, So, there will be the other integral now minus infinity to infinity, y from minus infinity to infinity, and this integral is a function of z alone. So, for a particular z, this will be your probability distribution. Okay. Next, how about the probability density? One way is just to differentiate this with respect to z. I do not know whether you know it or not, but if you differentiate it with respect to z, what do you get? See, the entire thing is a function of z alone. Okay. This integral remains as it is. This integral goes, okay, because this function when integrated with respect to x and limit z put, you get something with z. So, if you differentiate, this integral will go, of course, and x is to be replaced by z minus y. Okay. This integral will remain, because this is with respect to y, and if you differentiate, the outer integral remains, this inner integral will go, I repeat again, you are integrating this with respect to x and then putting the limit z or z minus y. So, if you now differentiate it back with respect to z, you get back the same thing. Okay? Only thing is x is to be replaced by z minus y. So, you basically get okay. So, this is a function of z alone. So, this gives you sorry okay. Now, suppose that means this probability density p x comma y is nothing but p x into p y. So, in this integral it becomes p of, so we can say p x just to differentiate now, p y y, and this integral I am sorry there will be no dx, I am very sorry, because I told you you are differentiating with respect to z. So, you should get back p of x comma y with x replaced by z minus y. Okay, so, that integral with respect to x gone means dx gone. So, no dx here, only single integral. Okay. Okay. Look at this integral. This is a famous integral called convolution integral. Okay, there are two functions p of x, p x and p y. P y, y comes here. In this case, this function, the y comes with a minus sign and it is evaluated at z. So, z comes here. Okay, this is a famous convolution integral which I think you are familiar with, because convolution comes very frequently in the description of linear time and invariant systems, both continuous and discrete. These integrals which is corresponding to a continuous system. Okay. Actually, this integral means what? How to carry out this integral graphically, in case you have forgotten. I rewrite the integral first again. This is for a given z, and then p y how to carry out this integral graphically. Okay. You plot say p y y, some function. And remember, p x z minus y, you can write it as p x minus of y minus z. So, first plot this function p x minus y, you can call it, give it even a name. P say 1 y, you can call it say P 1 y. Okay, you get some function. Okay. Maybe I should not draw the function same shape for both the functions. Maybe suppose it is like this, but you want to evaluate this function at z. So, it should be P 1 y, sorry, this is so it will be P 1 y minus z. So, you have to shift it to the right by z if z is positive, or shift it to the left by z if z is negative. So, you shift it by z and then you multiply this function and this function. See the overlapping area, multiply them and integrate. That will give rise to this integral. This is a typical way of, a very standard way rather, of carrying out convolution integral. So, in the next class we will carry out some example, okay, of this, that is two random variables x and y, okay, and they are having some particular probability densities for each. You form a random variable z as a summation of x and y. Okay. What sort of shape, what sort of probability density function you will have for z? Okay. That we will evaluate by carrying out this convolution integral. Okay. So, that is all for today. We start from here in the next class. Thank you very much. Okay. In the last class, we started with this topic function of two random variables. We continue from there. In fact, I take up the same example which I touched upon in the last class for some reason. That is, suppose it is given that where x and y are two random variables, okay, and z is a summation. We have to find out. So, z is a function of x and y. So, we have to find out the probability density of probability distribution and also probability density of this variable z. Now, how to do that? We recall